Forces and Motion by Marcia K. Miller. What happens when forces act on objects? Forces. How can a big elephant balance on a small ball? The elephant stays up because of forces acting on the animal and on the ball. A force is a push or pull. Forces have both size and direction. Some forces act only if objects are touching each other. Suppose you use your hands to push a heavy box. Your hands and the box touch. The elephant in the picture touches the ball, pushing down on it. Other forces act between objects that aren't touching. When you jump up, Earth's gravity pulls you down. Objects with an electrical charge can attract or repel each other even when they are far apart. Hold two magnets close together. They push and pull on each other even though they are not touching. Scientists measure forces in units called newtons. 1 newton is the force needed to change the speed of a 1 kilogram object by 1 meter per second each second. It takes about 1 newton to lift a small apple. You can use a spring scale to measure force. You attach an object to one end of the scale and hold the other end. A spring inside the scale stretches. This shows the force needed to support the object. Forces on objects. A kite flies through the air. It dips and glides. Different forces act on the kite. The weight of the kite pulls it down. The force of the wind pushes it up. You can change the direction of the kite by applying force to the string. Most objects have more than one force acting on them. Some forces act in the same direction. Other forces act in different directions. The effect of the forces on an object is found by adding together all the forces acting on the object. The forces acting on an object are similar to a game of tug-of-war. One team pulls the rope one way. The other team pulls the rope the other way. If one team pulls with more force than the other team, the rope moves toward the stronger team. If both teams apply the same amount of force, the rope doesn't move. Unbalanced forces on an object at rest can make it move. They can cause the speed or direction of a moving object to change. Balanced forces do not cause any change in motion. This is true even if an object is already moving. The downward force of a water strider on the water is balanced by the upward force of the water. The force of the wind against the sail causes a sailboat to move through water. You add the forces together to find the overall effect of forces acting on an object. The result is called the net force. Here's how it works. Suppose a 5 Newton force pulls an object to the right. A 3 Newton force pulls it to the left. The effect is the same as a 2 Newton force pulling to the right. The net force is 2 Newton to the right. The net force on an object may not always determine the direction the object moves, but it determines the change in an object's motion. Suppose you are riding your bike on a flat sidewalk. You lightly apply the brakes. What happens? The bike continues along the sidewalk as the force of the brakes acts against the bike's forward motion. The bike keeps going, but more slowly. A stronger force could stop the bicycle. Friction. A soccer ball slows down as it rolls across the ground. This is due to friction. Friction is the force that resists the movement of one surface past another. The ground is rough. Its surface stops the soccer ball by pushing against it. Friction acts in the opposite direction of the ball's motion. There are 3 types of friction. Rolling and sliding friction act on objects in motion. Rolling friction slows the spinning of a skateboard's wheels. Sliding friction makes it hard to push a heavy box along the floor. When you first push the box, static friction resists its movement. The box is easier to push once it starts moving. Static friction is usually stronger than sliding friction. Friction varies with the kinds of surfaces that are rubbing against each other. It also varies with how strongly they push together. Even smooth surfaces have tiny rough spots. Most surfaces have tiny bumps and holes on them. These rough spots catch on each other and cause the surfaces to move more slowly. Movement also slows when the particles from the two surfaces attract. The attraction causes the surfaces to stick together. There is usually more friction with rougher surfaces. A soft or rubbery surface also has more friction because it bends. But even very smooth and flat surfaces have friction between them. Their particles attract, causing friction. The floor of a bowling lane is very smooth. This reduces the rolling friction between the wood and the ball. Helpful and harmful friction. Friction can be useful. Suppose you were walking across a room without friction. It would be like walking on ice. You need friction between your feet and the floor so you won't slip. Drivers use friction all the time. When a driver steps on the brakes, the brake pads press against the brake drum. This friction slows the car. Sometimes friction is harmful. Think about what happens when objects rub together. Heat is produced. How do your hands feel when you rub them together quickly? They start to feel warm. Energy from your hands is converted into thermal energy because of the friction. Engines may not run well because of heat produced by friction. Friction between wind and soil can cause erosion. Friction from the road wears away the rubber on car tires. How does gravity affect objects? Gravitational force. Life on Earth depends on gravity. Throw a ball into the air. You know it will fall back down. Earth's gravity pulls all objects on Earth toward its center. Gravitational force is the force of attraction between any object and every other object in the universe. This force keeps the water in the oceans. It keeps the air near Earth. It affects how plants grow. It affects how your bones develop. Isaac Newton was an English scientist in the 1600s. He realized that gravity depends on the masses of the objects that apply forces on each other. An object with greater mass has stronger gravitational pull than an object with less mass. Hold this book in your hand. It pulls on you with a gravitational attraction. You pull on it too. You don't feel the pull of the book because both you and the book have low mass. But Earth has great mass. That is why you feel Earth's gravity. The Moon has less mass than Earth, so its gravitational force is weaker. The Moon's gravity is about 1/6 the gravity of Earth. An object with a mass of 100 kilograms weighs 980 newtons on Earth, but only 160 newtons on the Moon. Newton also found that gravitational force changes with the distance between two objects. Objects farther apart have less pull on each other than objects that are close together. Earth's gravitational pull is slightly less when you are in an airplane than it is when you are on Earth's surface. You can measure Earth's gravitational pull on your body. How? Just weigh yourself. Remember, an object's mass is the amount of matter it contains. Mass is the same wherever you are in the universe, but weight changes depending on where you are. You weigh more on Earth than you would on the Moon. Weight is another force that can be measured in newtons. Gravity and the universe. Newton's theory showed that gravity is what makes the planets and the stars move. The Moon revolves around Earth because of the gravitational pull between them. What keeps Earth and the planets in orbit around the Sun? It is the gravitational pull of the Sun. The Moon and planets would fly off into outer space without that pull. Earth and the other planets have much less mass than our Sun, so the pull of the planets does not have much effect on the movement of the Sun. Some planets in other solar systems have masses much closer to the masses of their stars. In those cases, the gravity of a planet can make a star wobble. Astronomers use this wobble to find distant planets. The force of gravity is different on every planet and moon. The mass of Mars is about 1/10 the mass of Earth, so you might think gravity on Mars would be 1/10 as strong as Earth's gravity. But because Mars is smaller than Earth, the gravity on Mars is about 1/2 the gravity on Earth. The gravitational pull of a planet depends on the distance from the surface to its center. This is also why you can't feel the Sun's gravity here on Earth. The Sun is much larger than Earth, but it is also extremely far away. Because you are so far from the sun, you feel only Earth's gravity. Tides. Water levels rise and fall near the ocean shores. These events are called tides. Each day, coastal areas around the world have 2 high tides and 2 low tides. The moon's gravitational attraction pulls on everything on Earth, including water. When this happens, we experience high tide on that side of the Earth. At the same time, the side of Earth opposite the moon also experiences high tide. While the sides toward the moon and opposite the moon are experiencing high tide, the 2 sides in between are experiencing low tide. The sun also pulls on Earth's water, but because the sun is farther away, the effect is smaller. How can you describe motion? Observing motion. Riding a roller coaster can feel similar to flying. You rise up, swoop down, and turn over and under. What do you see as the roller coaster moves? When you move closer to the ground, objects seem to be moving toward you. When you move higher, the objects seem to be moving away from you. How is this possible? The way to describe motion depends on a frame of reference. A frame of reference is any object that can be used to detect motion. On a roller coaster, your seat may be a frame of reference. You are not moving compared to the seat. You and the seat move together. What if you use the ground as your frame of reference? It seems perfectly still. Your seat moves in reference to the ground. When describing motion, Earth is usually a frame of reference. If you are sitting still, you aren't moving relative to Earth, but Earth is moving relative to the sun, and so are you. Earth moves through space. It also rotates on its axis. Yet you aren't aware of these motions because the objects around you are also motionless when Earth is the frame of reference. Kinds of motion. Circular motion is movement around a central point. A seat on a Ferris wheel has circular motion. The central point for the seat's motion is the axle of the ride. A looping roller coaster also has circular motion. So do planets in orbit and the wheels of a bicycle. As the bicycle wheels turn, the bicycle itself moves in a straight line. You can see straight line motion as you watch a parade move down the street. Vibrational motion is harder to observe. A vibration is a rapid back and forth movement. The strings on a guitar vibrate to make sounds. Your vocal cords vibrate when you speak. With the ground as your frame of reference, you would say that the seats of the Ferris wheel are moving. When you ride a Ferris wheel, the seat is your frame of reference. The ground appears to move. Calculating speed. Speed is a measure of how fast an object is moving. You can find speed by dividing the distance traveled by the time needed to go that distance. Suppose the bus in the picture takes 10 minutes to travel between points that are 9 kilometers apart. Use this equation to find its average speed. Average speed equals distance divided by time, equals 9 kilometers divided by 10 minutes, times 60 minutes, divided by 1 hour, which equals 54 kilometers per hour. The speed of 54 kilometers per hour is the average for the whole trip. But the bus probably didn't travel at exactly that speed for the whole time. Speed at any moment is called instantaneous speed. This is the speed shown on the speedometer. Velocity. The distance the bus travels on the return trip is the same. So is the travel time. But the direction of motion is different. Velocity is the speed of an object in a particular direction. The velocity of the bus on the first trip was 54 kilometers per hour east. On the return trip, the velocity would be 54 kilometers per hour west. The velocity of an object changes constantly as it moves along a curved path, even if its speed stays the same. Velocity changes because the direction of the object changes. Acceleration. Moving objects often change their speed and direction. The rate at which velocity changes is called acceleration. Acceleration doesn't happen only when an object speeds up. It also happens when an object slows down or when it changes direction. A force must act on an object for the velocity to change. So acceleration takes place when unbalanced forces act on the object. What are the laws of motion? Studying motion. People have wondered about motion for thousands of years. They have tried in many ways to explain it. In the 1600s, Italian scientist Galileo Galilei studied falling objects. People then thought that objects slowed down and stopped on their own. They did not know about friction. Isaac Newton published his book Principia in 1686. He linked forces to the motion of objects. Newton didn't discover all the laws of motion, but his book put together many important ideas in a way that people could understand. First law of motion. Newton's first law states that an object at rest remains at rest. An object in motion remains in motion at constant speed and in a straight line unless acted upon by an unbalanced force. You already know the first part of this law. Put a book on your desk. The book stays in place until you pick it up or another force acts on it. The law also says that objects stay in motion. But motion in daily life doesn't seem to follow this law. If you kick a soccer ball, it moves for a while, but it will slow down and stop. You have to keep pedaling to keep your bicycle moving. Why? One reason is friction. Friction can slow or stop objects in motion. The ground applies a frictional force on the bicycle wheels. Air friction slows motion as air pushes against the bicycle. Gravity and other forces may also slow an object's motion. Inertia. Newton's first law of motion is often called the law of inertia. Inertia is the tendency of an object to stay at rest or in motion unless a force acts on it. Inertia lets an ice skater glide a long way. Ice has little friction to slow the skater down. Inertia keeps a rock on the ground still. Suppose you have two jars that are the same size. One is full of feathers. The other is full of coins. The jar with the coins is harder to move. Why? The jar of coins has more mass. The amount of inertia an object has depends on its mass. The greater an object's mass, the greater its inertia. This crash test dummy shows the effect of inertia. When the car stops suddenly, the forward motion of the dummy continues. The force that stopped the car does not stop the dummy. The force of the seat belt and airbag stops the dummy's forward motion. Second law of motion. According to Newton's second law of motion, a force causes an object to accelerate. The acceleration of an object depends on the mass of the object and the strength of the net force applied. An unbalanced force makes an object accelerate. Look at the dogs in the wagons. The large dog has greater mass than the small dog. Only a small force is needed to pull the wagon with a small dog. The wagon with the large dog will not accelerate as much if the same force is applied. When equal force is applied, an object with greater mass will accelerate less. Suppose you push the wagon with the small dog. It rolls. If you push the same wagon harder, it rolls faster. An object's acceleration increases as the net force increases. The acceleration decreases as the net force decreases. Using an equation. This equation shows the second law of motion. Acceleration equals force divided by mass. Only unbalanced forces accelerate an object. Suppose you and a friend push on opposite sides of a box. You use the same force. The box won't move. But if one of you pushes with more force than the other, the box moves. It accelerates in the direction of the greater force. Third law of motion. When you throw a ball on the ground, it bounces upward. But the force of your throw was downward. Newton's third law of motion explains how this happens. When a force is applied to an object, the object applies an equal force in the opposite direction. The ball you threw on the ground exerts a downward force on the ground. The ground exerts an equal but upward force on the ball. Newton's third law of motion is sometimes called the law of action and reaction. For every action, there is an equal and opposite reaction. Before a leopard jumps, it bends its legs and pushes very hard against the rock. The rock exerts an equal force, pushing the leopard into the air. The leopard's push is the action force. The rock's equal but opposite push is the reaction force. Newton's third law of motion explains what happens when the two objects collide, or hit each other. Think of a basketball rolling along the floor. It hits a bowling ball that is sitting still. The bowling ball has greater mass than the basketball does. The basketball rolls back away from the bowling ball. The bowling ball only moves a short distance. Momentum. Momentum is a measure of the force needed to stop a moving object. It depends on mass and velocity. Momentum from one object can be transferred to another object when they collide. The total momentum before a collision equals the total momentum after the collision. This is known as the law of conservation of momentum. The momentum of the basketball before it hits the bowling ball must equal the momentum of the basketball plus the momentum of the bowling ball after the collision. The basketball slows down because it gives part of its momentum to the bowling ball.